So we now have algebraically solved our problem. Maybe we want to visualize it as an example. So initially we are at here 0, 0 when the non-basic variables are x1 and x2. So they are all 0. After one iteration, we move to another basic feasible solution, which is 4, 0 for x1 and x2. Okay? At that moment, your x3 is also positive, but regarding the original solution, you do not need to take a look at x3. So after one iteration, we move to 4, 0, 0. After two iterations, we move to our second solution if you do not count the initial one. So we move to 10 over 3 and 4 over 3. By simplex method, we conclude that it is optimal. Graphically, we may also see that it is indeed optimal. All right. So this not just verifies the solution's correctness, it also visualizes how we move along edges to search among extreme points. It's not just true for this particular example, it's true for all the linear programs. As long as you use the simplex method to move along basic feasible solutions, graphically you always move along edges. Okay? So to summarize all the things we just did, to run the simplex method, first we need to find an initial basic feasible solution with its basis. In general, we haven't told you how to do that, but very quickly we will show you how to do that. And then among all those non-basic variables, we take a look at the zeros row to see whether we may find the coefficient with the right sign. If we are talking about the minimization problem, we look for positive coefficient. If we are talking about maximization problem, we look for negative coefficients, as in our example. If the non-basic variable has the correct sign, we choose one to enter. Up to here, we haven't told you how to choose one to enter. It turns out that if you want to run the simplex method, this is an issue. Okay? Sometimes you may think about, well, how about this? I'm going to choose the one with the most significant coefficient. So what do we mean by most significant? If you have -2 and a -3, the -3 has a larger absolute value, and you may consider that as most significant, all right? But we know this is not always the best, because when you try to increase your z value, even though -3 tells you that when you increase that variable by 1, your z is going to be increased by 3, which is better than 2. But you have no way to tell what's going to happen if you increase x2 by 1 or 2 or 3 or whatever. You have not looked at the constraint. You don't know how far you may move your solution by increasing x2. Okay? If you really need to do that, you need to look at the constraints at least. So there is no way to say that entering x2 is definitely better than increasing x1. Okay? Entering x2 is not necessarily better than increasing x1 if you just look at their objective coefficients. So I hope that makes sense. So in practice, people actually don't really look at the most significant coefficient. People typically suggest you, for example, to just use the indexes. If x1 and x2 are both okay, then let's just pick x1. It's actually a more widely used algorithm or implementation to run the simplex method. So the reason cannot be told at this moment, but anyway, being able to select one variable to enter when you have multiple candidates is an important issue. And if you don't want to learn more, I would suggest you just to pick the one with a correct sign and the smallest index. Okay? So after we do that, we need to do some kind of ratio test from the basic and the right-hand side columns. one basic column would be considered to be the entering column. Okay, so actually what we are talking about is the column for the entering non-basic columns. Okay, so we have one entering variable. For that entering variable is typically non-basic. Okay, non-basic. So for that non-basic column and the right-hand side column, we would do the ratio test to determine which basic variable should leave. Again, there may be a tie-breaking thing that we need to consider. If the right-hand side columns and the denominator columns or the entering columns, if the ratio has some tie so that you have multiple numbers, not multiple basic variables hitting 0 at the same time, you somehow need to make a decision about which one to leave. Again, if you have no way to tell, I would suggest again the smallest index. Take a look at each basic variable which hits 0 for the first, and then pick the one with the smallest index. Okay, that's the idea. If you have some denominator which is 0 or negative, should you do that? Should you do the ratio test? I hope you also agree that we don't need to do that. Why is that? Because that somehow means when you increase that particular entering variable, this denominator being 0 means it has no impact on that particular basic variable. Or if it's negative, that means that basic variable actually also increase when you increase that non-basic variable. So in either way, there's no way for this variable to hit 0. You should ignore them directly. So once you do all of this, we would find a new basis. And then we need to make the system fit the requirements for basic columns. We need to have an identity matrix for constraints, and we need to have zeros in the objective function. Once we fix the constraints, we fix the system with elementary row operations, we redo everything until we are done. So that's the general way of running the simplex method.